Today we're going to learn the integral and the P series test. We're going to start with the integral test, and then the integral test is going to help us find some patterns for what our P series is. Okay. What do you think the integral test deals with? Integrals. Okay. I will tell you that the integral test is the test that is going to take us the most effort to use. That's not a bad thing. I'm just letting you know. I'm going to go ahead and let you write this down. And then we will move forward. We'll talk about it, but writing and tracking it this week. I wondered about that. This needs to be an N. Right there.
Does N always have to equal 1 for the equation?
No. You will, well, at least 1. Sometimes it'll start at 2. Like especially if we have the natural log of N, sometimes it'll start at 2.
Does that 2 then change the integral?
Whatever is here goes to the integral. Good thing we went through chapter 7. Chapter 7, we talked about those improper integrals, right? Was that chapter 7? I think it was. What was chapter 8?
No, 8 was integrals.
Chapter 8. In the old days, it was chapter 7. They like inserted a chapter. Okay. So first of all, as long as we are positive, continuous, and decreasing for our function, yes, those are 3 things that I have to see that you accounted for. Positive, continuous, those are really just things that you're going to think about. Decreasing, you better show me your function is decreasing. What would be a really easy way to show me that?
Take the derivative.
Take the derivative, make sure it's positive. Okay? Once you've made sure that our function is going to be continuous, positive, and decreasing, then we can convert our series to an improper integral. If this improper integral converges, well, then so does the series. If this improper integral diverges, well, then so does the series. Okay? Here's the thing, though. With these 2 tests over here, geometric and telescoping, we could figure out where we were converging to. That is not the case here. We just know whether it converges or diverges. We do not know the value in which it converges to. Only geometric and telescoping gave us those. Okay, so we're really just determining whether we have a function that converges or diverges. Excuse me, not a function, a series. So we're going to start off light. Okay. There's our first series. Okay. If you decide to use the integral test, then you need to first write it as a function of x. Okay. You then need to show me that this is positive, continuous, and decreasing. Okay, These first two, we just think about. Is e to the negative x positive? Yep, all the time. Is e to the negative x continuous? Yep, all the time. Now, maybe it's not continuous at like x equals -5. Doesn't matter as long as we're continuous in like this interval. Okay. Decreasing. All right. You need to show me the derivative. Well, our derivative is negative e to the negative x, which is always less than 0. Since our derivative is always negative, our function is always decreasing. We're good. Well, the derivative, yes. Because we want our function to be decreasing, right? Okay, then once we figure that out, now we can change our, instead of thinking about a series, we're going to think about our improper integral. Okay. And this is important. If we have an improper integral, we do have to rewrite it as a limit. Okay. So we're going to change infinity to be a letter like a. And now we have the limit as a approaches infinity. Okay, so our antiderivative would be negative e to the negative x, right? Evaluated from 1 to a. Bless you. So when we actually use the fundamental theorem of calculus, which I got to teach to my AB kids today, they finally know that shortcut. Negative e to the negative a minus negative e to the negative 1. Yeah. Okay. Towards infinity, what happens to this negative e to the negative a function? Goes to 0. So our limit is e to the negative 1. Since our improper integral came out to be a number, we say that it converges to be 1 over e. Okay, this is infinite area. So say that this converges. Okay, which means our series also converges by the integral test.
So the integral converges at 1 over e, but we just know that the series converges, we don't know where.
Correct. Correct. Did everybody hear that question? The integral converges to be e to the negative first. But that only tells us that their series, just don't know what to do. Jacob. So when we have an improper integral, like we can't evaluate an integral with infinity. So we had to rewrite it as a limit where we replace infinity with a letter. Okay. Other questions? Okay. Do you see what I mean that the integral test talk about? Okay, and that will continue to be the case. So I would encourage you, if you don't have to use the integral test, I wouldn't. Did we have to in this case?
Yeah, that was yeah, number 2.
Oh, we could have written that as 1 over e to the n.
Yeah.
Yeah.
So you didn't have to use that in this case.
If it were me and I had the choice, right? If I had a choice, I would write this as 1 over e to the n and use just a simple, it's geometric where absolute value of r is less than 1, it converges. Okay. Now, I just wanted to show you, this was a nice example to show, but you don't want to do this if you don't have to. Okay. This one, we have no choice. This is a series in some way, shape, or form you're probably going to see again. Notice how we're starting at 2.
Sorry. So the question on this one be, does it converge or not converge? Like, it wouldn't ask you to figure out where.
Bless you. Okay, so this one, we're not going to have a choice, and it's going to come back again, just FYI. So if we're going to use the integral test, we would want to write it as a function of x first, and make sure that it is positive, continuous, and decreasing. Okay, now, the natural log of n over n, as long as we're at 2, I guess I should say x, the natural log of x over x, is that going to be positive if we're 2 and above? That's going to be fine. Now, some of you thought it was weird that it started at 2. Well, it had to if it's going to be continuous. We can't plug in 1 to our series because it would make the denominator 0. Oh, wait. No, we could. Ignore me.
But then it wouldn't be positive, right? If we plugged in 1.
Yeah, it wouldn't be positive. Okay, but 1 would be fine for continuous also. Okay, we don't have continuity at 0, but that's not a problem. We're starting at 2. Okay, decreasing. We get to take this derivative, which would be 1 over x times x minus the natural log of x times 1 all over x squared. Okay. After 2 is this derivative negative? It is. Okay. So I have showed positive, continuous, and decreasing. Perfect. Okay. So now we have the integral from 2 to infinity of natural log of x over x, which we are going to write as the limit of our integral since we have an improper integral. Like already we've done more work than we had to with most of the other series tests that we've had. Okay. Antiderivative for natural log of x over x. It doesn't have to be parts. We would have to do use substitution in order for us to get there. Okay. If u is the natural log of x, then du is 1 over x dx, which we have right there. Okay, so side note, this is the integral of u du, right? So we have the limit as a approaches infinity of, our antiderivative would be 1/2 u squared. Okay, are you okay that I just made this little side note and I went straight to 1/2 natural log of x squared? Like that's okay. All right. So now we can actually use the fundamental theorem of calculus here. We have 1/2 natural log of a, the quantity squared, minus 1/2 the natural log of 2, the quantity squared. And you're thinking, yuck, I don't want to deal with all these numbers, but the natural log of a towards infinity. Infinity squared, still infinity. Whoa, those are the real quizzes. It's fine. So this diverges. Yeah.
Theoretically, if the second term was for some reason infinity, wouldn't you have to do like full log constant?
Yep. But that's not going to happen, like, because you're always going to have a number. Yeah. Yeah. So since this diverges, then our series also diverges by the integral test. Thank you. Which one, the series or the integral? The integral diverges because our limit is infinity. And if our limit of the fundamental theorem of calculus is infinity or negative infinity, then we say that the integral diverges. Yes. Okay, because when we talk about an improper integral, definite integrals is area under the curve. Okay, so when we're talking about infinite area under the curve, it's either going to converge to be a value, or like, oh, this is the area, or it's going to diverge to be more than we can count. Does that make sense? Okay. How do we go? Okay. I'm going to give you to do this one with the integral test. You and your buddy talk through it. You're doing a happy dance. You an answer?
Not yet. I'm still working.
Okay. Distracted by something here.
Yeah.
Okay. Maybe a bit distracted. Yeah, well, yeah. Yeah. I think everybody has it. But like the important, like that's not our answer. Like this is the answer that I'm wanting you to write out. Back to your buddy. Make sure you agree. Your work.
For the integral, I got one.
Okay, me too.
For geometric, it's a variable in exponents.
Yes. Okay, does your work look sort of mine? I said work, I haven't written my answer up. Okay. The decreasing part was nice, right? Right, that was nice. Okay. You have your integral set up. You change it to a limit because it's improper. Take the antiderivative. This one was nice. Apply the fundamental theorem of calculus, and then we get a limit of 1/2. So this is important. I really don't care that one. I care that it converges. And because it converges, then our series of n equals 1 to infinity of 1 over n cubed also converges. That says converges by the integral test. Okay, that is what I care about. Okay, your answer is a sentence with all of these that I'm asking you if they're converging or diverging. Okay, now that problem went smooth, didn't it? And I bet we could think about this problem where we just change the 3 to be a different number. Before we do, I want you to understand what a P series is. This problem that we just did is a P series. Okay, some of you are like, ooh, can we call it geometric? No, we can't call it geometric because our exponent needs to be the variable. Now our variable is being raised to some number P. Okay, and we're gonna have what's called the P-series test. Here in a moment, I will reveal it to you. But I want to talk about maybe what you think the rules are going to be. Okay, the integral test, we're basically going to like generalize for this rule. Okay, the integral test came first. And then we have this pattern. And you might have even, like if you think back to our integral, our improper integrals from chapter 8, you maybe even remember some of the patterns that we came across. Okay, so I'm going to come back up here to this one. This one converged, 1 over n cubed. What would happen with 1 over n to the 4th? It would converge. Okay, what about 1 over n squared? Okay, now I want you to think about 1 over n. 1 over n to the 1st. We would get to here, and what's the antiderivative? Natural log. What's going to happen with that one? It's not going to go well. Okay. 1 over n to the 1st, that's actually called the harmonic series. That one's not going to converge. That one's going to diverge. Okay. So this is our P-series test. Okay. I've broken it up into 3 different parts because P equals 1 is the harmonic series. It's special. But if P is 1, or if P is less than 1, then our series is going to diverge. If, like in our example above, and the ones we talked through, if P is bigger than 1, we are going to converge.
But we still don't have a way to figure out where.
But we still don't have a way to figure out what it converges to. And you're going to be really disappointed because most of our tests are going to be like that. Okay, we started out with the 2 good ones. Okay, now the integral test is a lot of work. If we can rewrite our series to be in the form 1 over n to the p, it is as simple as the geometric test. P is less than 1, it diverges. P is greater than 1, it converges. Okay, and that is all we have to do. Some of these might not even require work. Okay. Some of them, your work is going to be just rewriting the series to look like this, and then saying that it converges or diverges. Okay. P series and geometric series, your answers are going to look very similar, where you're just looking at a number and comparing it to 1. Okay. But in the P series, we want P to be bigger than 1. In the geometric series, we're looking at R being less than 1. Okay. So we'll finish out our day with a couple examples. So this one, the series 1 to infinity of 1 over n squared. Okay, first of all, we need to recognize that it's a P series. 1 over n to a power is what we're looking for. So this is a P series where P is bigger than 1. So we know that it converges. And that's literally all you have to do. This is one of the quicker ones, quickest one, probably. Okay. Now, here it's obvious. 1 over n squared, or our one previous 1 over n cubed, 1 over n. Sometimes we may have to rewrite our series in order to be able to use the integral test, excuse me, the p-series test. So instead of radical n over n, you would want to rewrite this as 1 over n to the 1/2. Now this looks like a p-series. Now you can say that, well, this is a p-series where p is less than or equal to 1, so we know that it diverges. No, if you started somewhere else, it'd be the same thing. Yeah. But it has to be 1 or greater. It couldn't start at 0. Oh. And the last example. All right. Okay, so the integral test, make sure you get all the moving parts. Make sure you check off the 3 pieces of the checklist and be very careful with your limit. Since we are having the limits of our fundamental theorem of calculus, it's possible that L'Hopital's rule could come into play. I don't know. I mean, just be on the lookout for that. Okay? Biggest thing is if you don't have to use the integral test, we don't really want to. Okay, now your book may instruct you to do it just so you get the practice, but when we get to make decisions, it's going to be like the bottom of our list. Okay. Geez, some of you already like packed up ready to go, and I'm done talking yet.